we were discussing about the property variations in isentropic flows, and let us work out a few problems to see that how we may evaluate those property variations. So, let us say that we have a tank like this, to which is connected one manometer. This tank has air at 30 degree centigrade, pressure is not known, the exit state from the tank is with a velocity of 235 meter per second. The manometer has the manometric fluid as mercury with a density of 13,550 kg per meter cube. The height, that is the difference in the levels of the limbs of the two limbs of the manometer, is 30 meter. Assume isentropic flow, that is given. You have to find out what is the pressure of the tank and what is the exit pressure and what is the exit Mach number. Okay. So, let us see how we may work out this problem. So, if we apply the energy equation in terms of the stagnation temperature, we have seen that T0 is equal to T plus U square by 2 Cp. So, when you have this large tank, remember that the properties of fluid, the fluid which is there in the tank is approximately at a stagnation condition. So, the temperature, the 30 degree centigrade, the air temperature within this large tank, this is the stagnation temperature corresponding to this condition. So, you have T0 is 273 plus 30 Kelvin. So, if you want to find out what is the exit temperature, so long as the flow is adiabatic one, you have T plus U square by 2 Cp, same as any T plus U square by 2 Cp. So, you can use the exit state here. So, let us say T exit and U exit. U exit is given as 235 meter per second. So, from here you can find out what is T exit. So, if you evaluate that, this T exit will come as 276 Kelvin. From the T exit you can calculate the Mach number at the exit, because the sonic speed at the exit is root over gamma r T exit. Remember that we are considering an isentropic flow for which this formula is valid. So, from here you can have the Mach number at the exit is equal to U by C, and if you calculate that, it is approximately 0.706. So, when you calculate the Mach number, you can find out from that the expression of P by P0. So, remember that we had an expression of T by T0 or T0 by T rather. For an isentropic flow, T0 by T was 1 plus gamma minus 1 by 2 m square, and P 0 by P so if we know the Mach number at the exit, so from here we can find out P 0 by P exit by using the Mach number at the exit, and the remaining relationship between P 0 and P exit. So, remember P 0 is nothing but P at the tank, right. So, the other thing is the difference between the P and the P at the tank and the P exit or the P atmosphere. Remember P exit is same as the P atmosphere, that is given from this manometer. So, P tank minus P exit is equal to the rho Hg minus rho air into H into G from the readings of the manometer. So, now you have two equations, one is P 0 by P exit, that is as good as P tank by P exit, another is P tank minus P exit. So, from these two equations you may solve for the two unknowns P tank and P exit. So, the answer to this is P exit equal to 101 kilopascal approximately, and P tank is equal to 140.8 kilopascal. Okay. Let us work out a second problem to illustrate the use of isentropic properties. So, this problem statement is like this: consider isentropic flow in a channel of varying area with the sections 1 and 2, between the sections 1 and 2, given the Mach number at the section 1 is 2 and given that V2 by V1 is equal to 1.2. This is given. What you have to estimate is the following: number 1 Mach number at 2, number 2 A2 by A1, and number 3 figure out whether the channel is converging or diverging. Of course, it might appear to be trivial by looking into A2 by A1, but you also have to make sure that there is no other type of variation in between. So, it has to be either monotonic or it may be area increasing and decreasing and so on. So, just A2 by A1 is not sufficient to tell you that what is the total shape of the channel in between 1 and 2, that is why the third part of the question, and the assumption is isentropic flow. So, if you see what is given here is V2 by V1. Let us see that how we may express it in terms of our known quantities. So, V2 by V1 is the sonic speed at 2 into m2 divided by the sonic speed at 1 into m1. The sonic speed is square root of gamma at T2 because it is isentropic flow. So, this is m2 by m1 into square root of T2 by T1. Okay. Now, T2 by T1 may be expressed as T2 by T0 divided by T1 by T0. Remember, T T1 is T0 is remaining fixed, this is isentropic flow. So, there is no question of any change of T0. So, you can write this as if you write for example T0 by T1, T0 by T1 is 1 plus gamma minus 1 by 2 m1 square divided by 1 plus gamma minus 1 by 2 m2 square, this whole thing to the power of half. Okay. So, in this expression what is given, V2 by V1 is 1.2, m1 is given. So, you have to find out m2. Of course, this is not a straightforward linear algebraic equation to find out, but one may find out by trial and error or by using some software such as engineering equation solver and so on. So, it is possible to find out m2 from this equation, and if that is found out, m2 turns out to be 2.98. This is by iterative solution. So, when you find out what is the value of m2, so the Mach number at 1 is 2, Mach number at 2 is 2.98, and how the area is increasing, if you want to answer the third part, let us use the expression of dA by A which we derived in the previous lecture. So, let us just write that expression. See, dA by A is this one, this is the expression that we derived in the previous lecture. So, if you see here, now the Mach number is between 2 and 2.98. So, the m square minus 1 is positive. Not only that, m is increasing, so from 2 to 2.98, so dm by m is positive. The denominator is always positive, that means dA by A has to be positive. So, it is an increasing A, it is a diverging section. And how to find out what is the real value of A2 by A1? So, A2 by A1 is nothing but A2 by A star divided by A1 by A star. Remember what is A star? A star is the equivalent area at which sonic condition could be achieved under an isentropic process. So, when the flow is isentropic, A star does not change. If it is not isentropic, the value of A star will change. So, A2 by A star and A1 by A star, these two may be found out. Again we have derived expressions for A by A star as a function of Mach number. So, from A2 by A star value you can find out, because you know what is m2. So, this you get from m2 and this you get from m1, and if you evaluate those expressions you will get A2 by A1 is roughly 2.46. If you use the compressible flow tables which are there in the appendix of the textbook, you will find that these values are tabulated A by A star as a function of Mach number. So, if you have a particular Mach number, you will get A by A star. Remember that it is just reproduction of the formula that we have derived in the class for gamma equal to 1.4 for air. So, if it is for any other fluid, you should have different tables for different fluids. The table which is there in the appendix of your textbook is for air. So, you may either use the table or you may use the formula to find out these expressions. Okay. Let us work out a third problem. So, it is given that this is the shape of a duct with the diameter at the inlet as 5 centimeter, diameter here that is D2 is 3 centimeter. The fluid is air with a stagnation temperature of 300 Kelvin, upstream velocity u1 is given as 72 meter per second. The pressure at the throat, that is P2, is 124 kilopascal, and assume isentropic flow. From that find out what is P1, what is M2, and what is the mass flow rate. Okay. So, first of all we know u1. So, if we know what is the sonic speed at 1, then we may find out what is Mach number at 1. Sorry. To find out what is the sonic speed at 1, what we should do, we should find out the temperature at 1, and to find the temperature at 1 we should use the energy equation. So, T0 is equal to T plus u square by 2 Cp. So, from here you know what is T0 that is given, you know what is u1 that is given, Cp of air is known, from that you can find out what is T1. So, T1 is 297.4 Kelvin. So, once you know T1, you know M1, that is u1 by square root of gamma T1, and that turns out to be 0.208. Once you know M1, you can find out A1 by A1 star, it is a function of M1 only. Okay. So, when you find out this one, from here A1 is given, A1 is pi d1 square by 4, this function of Mach number is known. So, from here you can find out what is A1 star. So, the value of A1 star is 0.0006886 meter square. If you calculate, that is what you will find out. Now, what is A2 by A2 star? A2 by A2 star is nothing but A2 by A star. Remember, A star remains same so long as this is the isentropic flow. So, A star has already been calculated, this is A1 star is same as A star, and A2 is pi d2 square by 4. So, by putting these values you will get this as 1.027, and this is a function of M2, and from this you can find out what is M2 by referring to the table of isentropic flows. So, M2 is, if you calculate this, this is 0.831. Once you know the Mach numbers, basically you know everything, because then you can use the expressions for P by P0, T by T0 like that. So, you can calculate P1 by P0, you know T0, therefore you know P0. From P0 you may now calculate P0 by P1 as a function of Mach number at 1. So, from that you can find out P1. So, you can find out P1 not from this one, but from Mach number at 1. So, so T0 will give you P0, I am just outlining the procedure. From the Mach number at 1 you have P0 by P1 as a function of Mach number from this what is P1. So, P1 if you calculate it is 189 kilopascal, and the mass flow rate, it is you can write rho 1 A1 U1 just as an example. You could also write as rho 2 A2 U2. Rho 1 is P1 by RT1 into A1 U1, all these things you know. So, you may substitute the values to get the mass flow rate, which is 0.313 kg per second. Okay. So, we can see that how you may utilize the properties of isentropic flows to calculate different quantities, pressure, temperature, mass flow rate under different conditions.